right, so I wanted to make a video that to me pertains to the chapter that we're in, chapter 13, where we're making a relationship between Newton's second law and using that to find equations of motion of an object. I'm not actually sure. I thought this was mentioned in this chapter, but I think it might not be. And so it's a little more physicsy, but I think it's still something you need to be aware of. So the idea is, what is the difference between an inertial and a non-inertial frame of reference? Just to note, I use FOR as an abbreviation for frame of reference moving on because it's a lot to write. So you might have heard those terms, an inertial frame of reference or a non-inertial frame of reference, and weren't really clear what they meant. And I wrote down sort of the basic definitions that are given, but I think especially for the inertial frame of reference, it doesn't always really mean a lot. So in the inertial frame of reference, usually what is said is an inertial frame of reference is a frame of reference where Newton's laws hold true. And like, I don't feel that that's a good explanation, but I wrote it down. But the idea is that when you're using Newton's second law and applying it to your scenario, all the forces that you're taking note of or talking about acting on an object are true forces, so things like weight and tension and friction and things like that, like real forces that we can understand how they're caused. So that's what an inertial frame of reference is. And then in contrast, in a non-inertial frame of reference, if you are going to be using Newton's laws, you find yourself introducing fictitious forces. And so the question is, what is that? Like the name sounds, it's forces that aren't actually real. A really good example of a fictitious force, which tends to be one of my pet peeves, is centrifugal force. Centrifugal force is not a real force. If you learned, hopefully, in general physics, the centrifugal force is actually sort of a side effect of the fact that you're accelerating, and it's a consequence of your inertia. So if you recall, when the times when we introduced this idea of centrifugal force would be, typically we're moving in a circle, and we feel sort of like we're being pushed out away from the center of the circle. The problem with that is centrifugal force alone is not adequate to describe what's happening, because when you get right down to it, you would want to say, well, what causes that? What is that force, Is it a normal force? Is it friction, Is it a push from a physical push that someone does? And the answer to all those questions is no. There is no real physical explanation of why you are being pushed outward, because it's not a real force. But what happens is you actually feel like you're being pushed out because you're trying to keep moving straight, but you're being constrained to a circular path. So for instance, when you or in a car, and the car takes the turn too quickly, your body wants to keep going forward, but literally the car turns into you, and as you're moving forward, you run into the side of the door. And so you think that you were pushed to the side of the door, but it was just your inertia. If I had said that this was caused by a centrifugal force, the centrifugal force would be an example of a fictitious force. It's not real. To further delineate between these two frames of reference, a quick thing to remember is that any frame of reference that is accelerating is non-inertial. And so that might help to understand why we are in a car going around a curve really quickly. You should remember that we would be experiencing centripetal acceleration. And so by virtue of that fact, we are in an accelerating frame of reference. And so we should expect that we can't explain everything using actual real forces because we're in a non-inertial reference frame. An inertial frame of reference would be anywhere where we find that it's not necessary to introduce some fictitious force. And another thing that is often pointed out is if you find an inertial frame of reference, any other frame of reference that's moving at a constant velocity relative to the first one would also be an inertial frame of reference. So a frame of reference moving with a constant velocity can be inertial, and it should be if it's moving at a constant velocity relative to an inertial frame of reference. If we get down to it, on Earth we actually aren't in any inertial frames of reference because we're rotating, the Earth is rotating on its axis, so we're always spinning, and we're also revolving around the sun. But if you actually calculated the magnitude of acceleration that we're experiencing because of either of those two motions, it's extremely small. And so it's okay to just say, yeah, we're inertial here. It's good enough. So I wanted to try to show a really simple demonstration. I don't know if I should call it a demo or what, but a really simple example of how we can compare two different frames of reference and how our outcomes are different for the two. So as physicists like to do, we're going to use a train car. We love the train car to illustrate things in physics. And if you're watching this, I hope you had relativity because that's where it happens. So we have a train car and the train car is accelerating. For whatever reason, there is a mass on a string hanging from the ceiling of that train car. And what happens is the train car accelerates, we should expect that that is going to become deflected. Now, we're going to have two different observers look at this scenario and explain it in their own way. We have a person who's standing outside of the train car, and because they are not accelerating, this person is in an inertial frame of reference. The guy in the train, however, is in an accelerating train car, so he is in a non-inertial frame of reference. So what we're going to do is we're going to look at a free body diagram for each person. And when I say a free body diagram, I guess it would make sense if I actually told you what the diagram was of. We're going to look at the mass on a string. So I have this mass on a string, and right now I'm going to look at it from the point of view of the person who's standing outside of the car. Now let's look at the forces that are acting on this mass. I got the tension acting on it from the string, and I have the weight mg acting straight down. So those are my only two forces that I have. And if I look at Newton's laws, in the x direction I do have acceleration because as the train car is accelerating, so is the mass. And the only x component of force I have is the x component of the tension, which because of the way that I've defined the angle is t sine theta. And so that's my x force. And in the y direction, it is not accelerating. And so I have the y component of the tension minus mg equals 0. All right, so those are the free body diagrams for person A. And then if we look at this, you know, I could use this equation here, the y equation, and find tension in terms of weight and substitute in here, but I don't really know that that's necessary. I don't think that's going to get us anywhere. But what I would like to point out is when we look at this, let's just talk about what it's telling us, because I think it's helpful. You know, the train is accelerating, and because of the fact that the ball and the string are attached to the train, they have to accelerate as well. But when we really think about what exactly is the force that causes this ball to accelerate in the x direction, it's the x component of the tension. That's the force that's causing that acceleration, because it's acting directly on the mass, and its x component helps it to move in the x direction. So let's look at the free body diagram for person B. Now things are going to look a little bit different, and what I want to stress is that, you know, what we're going to see might seem weird, but we're going to have to think about the fact that the second person doesn't know he's accelerating. I've created a magical train car where somehow person A can see inside of it and see what's happening, but person B cannot see outside, so he has no way to know that he's actually accelerating. I think we've seen examples of this, like when you talk about relativity, you think about the fact that when a person is in, whether it's a spaceship or a train or something that's accelerating or moving, the idea is that we don't allow them to have any sort of outside information to sort of confirm that motion. And so I also want to draw the free body diagram, and so I'm going to get rid of this right now because I forgot to draw the free body diagram for this person. So he still sees the ball at some angle theta, but this time he says there's a tension, there's the weight, and there's some force. Because if you think about it, person A knows that the reason that that ball is deflected is because of the acceleration of the train car. And in a sense, this is getting left behind. While this person, they're in the train car, they have no visual to look outside of the train car. So he doesn't know he's accelerating. What he does know is that by some magic, this ball that is attached to a string on the ceiling is deflected. The only way he can explain it is to introduce a horizontal force that pulls that mass off to the side so that it's not hanging straight up and down. And if we look at the forces in the x direction, for this guy, he's saying they add up to be 0 because I'm not accelerating. I have no reason to believe I'm accelerating, and so I have t sine theta minus f is equal to 0. And in the y direction, he doesn't see anything different from person A. And so this is a fictitious force. It's fictitious because the person in the non-inertial frame of reference had to introduce it in order to make his Newton's second law work, because he couldn't observe any acceleration, but he did see that ball being deflected. So he had to introduce a force. He wasn't really sure what it was, but it must be there because he sees evidence of it, again, because of the ball's deflection. If you compare these two expressions, it's actually interesting to note that when I look at this expression and this expression, I see that the magnitude of that force is equal to the mass of the ball times its acceleration. And so in some situations when we would look at different types of inertial frames of reference, the mass times the acceleration is sometimes called the inertial force. It's not really a force, but we call it that if we're dealing with a non-inertial frame of reference in the context of trying to make Newton's laws work. So, I hope that this is helpful to give you a deeper understanding of what the difference is between inertial and non-inertial frames of reference. It might take a little while to let it all sink in, but play the videos often as you need to, because I think it's a good thing to understand as a physicist.